Welcome to the Explainer. Today, we're going to talk about the unseen path of a projectile. It's a journey that's totally governed by these powerful, invisible forces, and we're going to break down the complex physics that get a bullet all the way from the muzzle to the target.
So let's just kick things off by tackling a huge misconception, one you've probably seen 1,000 times in movies. A bullet zipping along in a perfectly straight, laser-like line. But is that really how it works? The short answer? No way. Not even close. And the reason why is a pretty fascinating story of physics.
Okay, so to really get a grip on a bullet's true path, we've got to dive into something called external ballistics. This is basically the science of everything that happens the split second the bullet leaves the barrel. From that moment on, it's completely on its own, fighting against the forces of nature.
All right, so let's get into it, and the best way to do that is to picture two totally different worlds. First, a perfect world, like a total vacuum, no air at all. And second, our world, the one with our atmosphere. The difference between those two, well, it changes everything.
See, in a vacuum, a bullet's flight path is, well, it's perfect. A beautiful, totally predictable curve shaped only by gravity. But that's not our world, is it? Here you've got two big players constantly at work. Gravity, which is always pulling it down, and air resistance, or drag, which is always trying to slow it down. And that turns that simple, perfect arc into something way more complicated.
Let's break down that first force, gravity. Now, gravity causes something we call bullet drop. And, from the instant a bullet leaves the barrel, it starts falling. No ifs, ands, or buts. But here's the part that might just blow your mind. You'd think a faster bullet, or a heavier bullet, would fall differently, right? Wrong. It makes zero difference. If you could fire a tiny, super fast bullet and a big, heavy, slow one perfectly level at the exact same time, guess what? They would hit the ground at the exact same moment. Gravity just doesn't care about mass or how fast something is moving sideways.
And the effect here is, well, it's huge. Just think about this. In only half a second of flight time, any bullet has already dropped 4 feet. 4 feet! That's a massive, non-negotiable law of physics that every single marksman has to account for.
Okay, so we've got gravity pulling the bullet down and air resistance trying to stop it. How in the world did engineers solve for this? How do you design something that can fight both of those forces as effectively as possible?
Well, it's really a story of one innovation after another. You start with the simple sphere, totally unstable, loses speed like crazy. The fix? Rifling. Those spiral grooves spin the bullet, just like a quarterback spins a football, and bam, you've got gyroscopic stability. Then, to tackle air resistance, they came up with that pointed arch shape, the ogive, to slice right through the air. And for those really long shots, they tapered the back end into a boat tail to clean up the turbulence and reduce drag.
All right, so we've got this super engineered projectile. But how do you grade it? How do you put a number on just how well it flies? Well, that's where we get into the report card for bullets, so to speak.
First up is something called sectional density. The easiest way to think about this is how much oomph a bullet packs for its size. Imagine a badminton birdie and a golf ball that are the same width. Which one's going to fly farther when you throw it? The golf ball, right? That's because it has a way higher sectional density. It carries its momentum much, much better.
And that brings us to the real MVP, the Ballistic Coefficient, or BC. It's just one number that tells you everything about how well a bullet cuts through the air. And yeah, there's a formula for it. It looks at weight, diameter, and this form factor thing, which is basically a grade for its shape. All those cool design choices we just talked about, the pointy nose, the boat tail, this is where they get their A+.
But hey, you don't have to remember the formula. All you really need to know is this simple rule. When it comes to the ballistic coefficient, bigger is always better. It's the ultimate score. Exactly. A higher BC means that bullet is a master at defying air resistance. It holds on to its speed for way longer. And think about it, if it's faster, it's in the air for less time, which means gravity has less time to mess with it. So it flies flatter, faster, and the wind can't push it around as easily.
But even with a killer BC and a perfect spin, the flight path isn't, well, it's not perfect. Especially right at the beginning. As soon as that bullet leaves the barrel and hits the open air, things get a little shaky for a moment.
Right as it pops out of the muzzle, it's doing this little dance. There's nutation, which is that initial wobble, like a spinning top right when you let it go. Then there's yaw, where the nose kind of drifts off center. And precession is the axis of the bullet making a little circle. Now that gyroscopic spin from the rifling settles all this down pretty quickly, but for those first few moments, it's an inherent part of the journey.
And it's not just wobbling up and down, it's also moving sideways. You've got the obvious one, right? Wind drift. A crosswind just physically pushes the bullet. But then there's this other, sneakier one called rifling drift. That spin, the very thing that gives it stability, also causes it to ever so slightly move in the direction of the spin. So a right-hand spin, the bullet will drift just a tiny bit to the right over a long distance.
All right, so let's take everything we've just talked about, gravity, air resistance, bullet shape, and use it to answer a classic question, and it's a really important one.
So, you hear it all the time, right? Don't fire guns into the air. But is a bullet coming back down really that dangerous? Let's use some actual ballistics to find out for sure.
Okay, the whole answer boils down to one concept: terminal velocity. A bullet shot straight up will eventually run out of steam, stop, and then start falling. Gravity pulls it down, making it go faster and faster. But at the same time, air resistance is pushing up against it, harder and harder as its speed increases. Eventually, you hit a point where the push from the air perfectly cancels out the pull from gravity. It can't go any faster. That's its terminal velocity.
So how fast does something need to be moving to actually be dangerous? Well, the science shows it only takes about 150 to 200 feet per second for a projectile to break human skin. Honestly, that's not very fast at all.
And this is where it all clicks. Depending on its shape and weight, its ballistic coefficient, a falling bullet can hit a terminal velocity of 300, 400, even 500 feet per second. That's more than double what's needed to be lethal. So the answer to our question? It's a loud and clear yes.
So you see, this isn't just abstract physics. It has incredibly real consequences. The path of a bullet is this whole drama playing out in fractions of a second, a battle between gravity and human engineering, between chaos and stability. And it really makes you think, doesn't it? From something as simple as the arc of a baseball to the silent, massive orbits of planets, these very same invisible forces are constantly at work, shaping absolutely everything around us.